Hi friends, welcome to CodeNet, and today we want to understand how we can implement a stack via a linked list practically using a code. And I'm sure you can even tell from the actual screen we have a code which needs to be explained and how each and every statement, a statement is simply a line of code, how each and every statement can be implemented when we are implementing, of course, a stack using a linked list. And here you can tell that the first line, which is line 3, of course these other lines, you can tell that of course I'm just implementing a comment, and a comment is something that won't be executed by the compiler, or should I say by the IDE. So you can tell from here that yes, I'm saying include IOStream. This is a line which just denotes that we are including, of course, a certain file inside our C++ code, and it should be always it should be available in the syntax of a C++ program. And of course down you can tell I'm saying using namespace std. This line of code which is using namespace std just allows me to use the cin and the cout without the prefixing of the std before I write the cin and the cout. And down here you can tell that this is simply just the declaration, the very basic declaration of the linked list, like we even discussed from the session of linked list. So what I'm saying is, okay, I'm declaring the actual linked list, the actual format that a linked list that I will be making, a linked list that will be based on stacks, the one I will be implementing, the actual syntax that it should follow. So I'm saying, okay, this is struct, a keyword definitely from data structures. I mean, we are doing data structures, and then this is the actual name for the actual node that I will be making. The name should be descriptive, so I know a linked list just makes nodes. So this is why I'm saying, okay, struct node, that is the actual name for the actual things, which is the nodes that I will be making. And then this node should be having two parts. The first part is the part to hold the data, which is based on a simple data type, and the actual variable is called data. And then the second part is called next. Next is also more like a variable, but a special type of variable, because it's not based on a simple data type. It is based on definitely a pointer. This is why we are seeing a multiplication sign. So this is what I'm doing. I've created the syntax for the actual linked list that I want to implement via the use of stacks. A stack definitely follows the principle of last in, first out. So that has been done. So definitely down here you can tell that I've just implemented a comment saying I'm creating a global top variable. Now this variable is definitely a global variable because I want the top as a variable which is based on pointers. This is what this line actually means. And then struct, definitely we understand what we are doing, but when we say struct, and then this type of variable should be equal to now. For now, top as a variable when it comes to stacks via linked list works like the way the head works when it comes to the linked list when we are implementing them individually. So the top is the very variable that is based on the pointer, which will be keeping track of the memory address for the very first node, the node that will be next to it, the node at the beginning. It is the top that will allow us to traverse through each and every node of our stack via the linked list. So this is what we are doing. And then you can tell many people start to ask questions now, hey, but why are we implementing a stack via the use of linked list? Almost from our previous session we are learning on how we can implement a stack via the use of the arrays. I mean, let's understand our theoretical knowledge on why we are doing this when it comes to the implementation of stack using the linked list. Why via linked list than the arrays? One of the reasons why we should like implementing the stacks via the linked list than the arrays is the arrays create a stack. Yes, they do so, but they do so with a limited number of elements. An array is fixed. From our previous session, we implemented, of course, a stack with a fixed number of elements. It was up to 100, and it was so because an array should have a total fixed number of elements that it should work on. The second reason is with a linked list, elements are not stored in a contiguous memory. They are stored in the nodes. You see the importance of this reason as we proceed with our practical implementation. Then the third reason is, since linked lists are highly associated with the pointers, then it means we can use a linked list to dynamically allocate and deallocate memory of a stack. Hence, linked lists being a reliable implementation of the stacks. In a linked list representation from our code, we'll be using the top. The top is used to locate the top element of the stack. Last in, first out. The very top element in our container, will be denoting it, or will be keeping track of it using the top as a variable that will be based on a pointer. You'll see how we'll create this variable. Even though the top will be giving us the memory address for that top element of the stack, unlike from the arrays where we are just getting the actual element when we use top inside to denote the element that's at the very top. And some key terms that we'll find, in the terms that you might find difficult, are the terms underflow and overflow. We'll see what these terms are, but for now just understand that underflow, it's that point when the stack is completely empty, and overflow, it's at that point when the stack is completely full. Though when it comes to the implementation via a linked list, just know this theoretically, because practically, I mean, how would a stack be full if we are implementing it using a linked list? So we'll see the advantages even during the code as we explain the actual implementation. So another section of the code that we want to understand is how to implement the push function. A push is an operator which allows us to send in elements inside the stack. I mean, that's what we even discussed. So we are implementing a function which is a void function. A void function is that type of a function that doesn't need to return a value. If you want to understand how functions are and how they can be implemented, double check the description. There should be a link that will lead you to function in the course of Introduction to C++, which is the course we need to know before we come to data structures and algorithms with C++. Let's continue otherwise. So we are saying, okay, I'm making a void function with the name push. This is the name of the function, and this function should have a parameter that will receive an argument from the actual main function or from any function that will be sending that, of course, that value. So the actual parameter is implemented in the syntax of course, the variable value, which is based on a simple data type, and this parameter should be in between the parentheses. I'm sure you can tell. And this is the actual, now the main body of the push function. So we are saying, okay, in line 16, this is what this code actually means, and this is how we should be implementing this code in C++. We are saying, okay, I want to create another variable which is a node. So I'm saying a node because, I mean, the name should be descriptive, though you can give it any name. So I've named this variable which is pointer based, because this is what this means. This means it is a pointer based variable. So I'm creating a variable which is called a node, and immediately when we receive a value into the push function, immediately we receive a value, a new node should be created. Hence, this is what this key coding statement actually does. The new is a keyword, and we are using, of course, node because it is the actual syntax name that we implemented from the very declaration of a linked list, which we implement the linked list, which is allowing us now to work with the stacks as we implement the stacks using the linked list. So we are saying, okay, immediately when we receive a value, I mean, a node should be being created. A node is actually a name of a variable, and then immediately when we create a node, and the actual thing which will be allowing us to create a node is this statement which we are saying new node. We even open the parentheses and we end with the semicolon. So in C++, each time we want to create a node, we should never forget to use the keyword new. Actually, it's the new keyword which entails that we are working with dynamic memory allocation. So what do we want now? Okay, immediately we create a node. The node created, which is a node as the actual name for the variable, which will be denoting a node. I mean, a name should be descriptive. You can tell that it is even to descriptive, this name. So you're saying, okay, immediately we create a node. The first part of that node should hold on to data. And the content that should be at the position of data is value, because it is the value, the actual number that we've received into the push function. And on the second part, which is called next, it next should hold on to the memory address that top as a pointer variable is pointing to. If top is equal to now, I mean if we don't have any node, then also the first part of the node should equal to now, hence terminating the actual process. There should be no link because also top is equal to now. But how are we going to keep track of top? Because we said in linked list, even whether implementation of linked list using stacks or using queues, we'll understand on how a linked list can be implemented using the queues in our next sessions, whether in what type of data structure. Top should always point to the very first node of the linked list. So as at now we can say top should point to the very first node that we implement of a stack via a linked list. So this is why we are saying okay, and for now top should keep track of the memory address for a node that was created. And using this statement, definitely top will keep track of the link to the very first node since it is equal to a node, and they are all definitely pointer based variables, hence this can work out. Now another type of function that we want to understand is the pop function. The pop function denotes the actual operation of pop as a pop operation that can be performed on stacks. Pop removes out an element from the stack, the top element from the stack. So we are saying okay, I want to create a function which is a void type of a function. The name of this function is pop, and you even open the parentheses. We are not passing in any parameter inside this function because we understand that we don't need any parameter to pop out an element. The element on the very top will be popped out, and then we are saying okay, if top is equal to now, I mean if top is equal to now, if the content inside the variable that should keep track of the memory address for the very first node is equal to now, if the content is empty, then it means we don't have any value. See out stack underflow. This is what we discussed from our theoretical understanding. Whenever we hear the keyword underflow, it means the stack is definitely empty. So if it is empty, then yeah, just tell us it is empty. This is what this line of code actually tells us. Else, if it is not empty, meaning if top is not equal to now, then the popped element is the element on the top should pop out, should be printed out. So we are saying okay, this is the top element that has been printed out. We even proceed on advancing the linked list because this is what this line of code actually does. Top, of course, next, meaning we want to go now to the next node. If that node is printed out, again the number that has been printed out, we keep track of its link, and then we even proceed again to another node. So this is what we are saying. Now what else can we discuss in this session, especially on the implementation of stacks via the linked list? We now want to understand how we can implement another type of an operation which allows us to print all the content that are inside the stack using the linked list. So we want to do so using the function which is a void function, and here we're having the display, of course, as the name of the function, and the parameters, they don't need to receive any argument from the main function or from any function. And don't forget, we were saying top should keep track of the memory address for the very first node. That is a rule. It should always be like that. So meaning, for we to display the content inside the nodes, let's say we have 25 nodes, it means we can't use top to move through each and every node. Immediately when we use top, then we'll destroy the actual syntax for the implementation of stacks. Okay, on the next occasions when we would want to now move again, what variable will we use? we won't use any variable. Why? Because we already used top. We've destroyed the actual syntax. Hence, this is what this line actually is preparing us to. We are saying, okay, struct node as top. So I'm creating another variable, which is also a pointer variable. This is what this denotes, and of course we are doing data structure, which is struct as structure, and then we are saying, okay, I'm creating another variable which is named as top. I want this variable to hold on to the values that also top is holding on. It is getting a copy of top definitely into it as a variable, because it is a variable that we will soon use to traverse through each and every node. And then I'm saying, okay, if as top is equal to now, then okay, if it is equal to now, and I'm saying it should keep track of the element that also top is keeping track of. So if it is equal to now, then it means the stack is empty. Else, this one as top is equal to top. So meaning the content in top is the thing that we are taking to as top as a variable. This can happen. We can copy the content in top to as top as a variable. These are just names. You can give them any name because they are all pointer variables. Hence, copying is vital. It can be done. So we are saying, okay, if as top is equal to top, then we are saying, okay, elements in the stack are while as top is not equal to now, because it will traverse through, while the part on the node that holds on to the link is not equal to now. This is what this line of code is doing, and we are using a while loop. If you want to understand how a while loop can be implemented, double check the description. You'll be taken to the right video. Then see out as top on the very first part of the node. Each content on the first part of the node should be printed out, because we are using cout. We are even giving some space, and then we are even advancing the links, because we are saying as top should not just print out the value in the very first node. No, the value printed out, please get the memory address for as top, put of course on that position, and follow the operator as you print out the content in the next node. So this line of code simply advances the link, simply allows us to continue traversing through each and every linked list as we are implementing the stacks. And finally here we are now definitely just terminating the entire process, ending the line for we to proceed printing out the next content on our new line. So this is what we are doing here on the actual understanding. Now on the theoretical understanding, this is what is being done. So we are saying, okay, inserting and deleting of an element in stacks using a linked list should be done from the beginning. That should be done from the actual beginning of the actual code. So this is what is being done. Okay, if we want to create another node, we won't create another node on the far end from the tail. The end is called the tail. No. Why? Because it will take time. Even on time complexity, we would say, okay, this is big O of n. I like saying big O of n because I mean the O is definitely doing its work and everything related to that. But what it actually means is, if we were to insert a new node on the very far end, on the tail of the actual linked list that is being implemented using the stacks, then it means we have to move from the first node, second node, third node, and when we reach now the last node, we will get the memory address for the node that is to be implemented. Let's say if it's 80, now write the 80 on the very last node that was the last before the implementation of a new node, and then point now, this will point now to the last node, and then from there we'll say, okay, it's this node which is equal to now. But this is not, of course, a proper way of doing it. I mean, it might take time. For we to insert or to delete a value, we need to start moving from node 1, node 2, node 3, up to node, of course, 5. But with stacks, it's last in, first out. So it means if we are now to delete again the same value, since it's last in, first out, since it was the last one to be implemented, again we'll move from node 1, node 2, 3, up to the last one. We delete the last one, but the time complexity now, n for the number of nodes, meaning if we have 20,000 nodes, then we'll move node 1 up to the 20,000th node. That's when we delete the node that is next to it. And inserting and deletion of elements when it comes to the stacks is always done from the beginning, because at the beginning the time complexity is big O of 1, meaning no need to move through each and every node. If we want to insert a new node, if it's from the beginning, then we'll make a new node from the actual beginning, and then we'll point, of course, head to the newly created node, and the newly created node is the node that will hold on to the memory address of the very first node, the node that was the first node before its implementation. Hence we have 6 and then 7 in this node, and then here we have the data that will be sent to this node, and then here, if this is of course at memory address 12, then head will just change its memory address to 12, and definitely this will be done. And then this, instead of pointing now to now, will point on to the second node, meaning the node that was created before the creation of the newly created node. So this is how the insertion and deletion actually does. Let's go back on our code. We see and understand more on the code that is being used to implement the actual data structure which we are working with using a linked list. So this is the main function now. The main function is simply the function that will drive the entire process. What we are saying is, okay, int option and int val, standing in for variable. We are just declaring two variables, and from here you can tell that we want this to be menu driven. We have of course the code that will make this as a menu driven code and anything related to that. So we are saying, okay, if the user enters 1, then he or she will be taken to the function that will allow him or her to push in a value. If a user enters 2, definitely it's to the pop function. If the user enters 3, definitely it's to the display function. If the user enters 0, then it's to terminate the entire program. So we've implemented a do while loop. You can tell that this is a do while loop. And the last statement in our while loop simply adds on the actual condition, which entails that if the value entered by the user, which will definitely be being entered on the option as a variable, if it is equal to 0, because it should not equal to 0, then the program should definitely terminate. And this is what we are saying. Okay, so enter a choice. Enter a choice allows a user to enter a value into the option as a variable, then option of course cin, and we are saying, okay, now using a switch statement. If you want to understand how a switch statement actually works, please double check the link. You'll be taken to the respective course that will teach you how a switch statement actually does. So what we are saying, okay, if the user enters the option, then that same value which is in the option should test the cases that are available. If the value is 1, then a user will be asked another question. Okay, enter a value that you want to be pushed into the stack that you are implementing via a linked list. So of course cin val just denotes or gets the value that we want to insert inside the stack, and immediately that value is entered, then a push function will be called. This argument will be sent in the parameters on the push function, because this is what we actually did. We even set the actual variable that will be receiving the values from the main function. So if the user enters 15, then 15 will be sent into the stack. If again the operation iterates, the user enters option 1, again we ask for a value. If the user enters 27, that 27 will be sent into the stack using the push function, and from here we just break, of course, the normal breaking which would be done when we are doing the switch statement. But if the user enters option 2, then we'll just call the pop function. The pop function is simply the function that will just pop out or simply remove the element that's on the very top of the stack. But what if the user selects option 3? If the user selects option 3, then he or she, that's the user, will be taken to the display function, the function that will display all the elements. That's if the elements, they are inside the stack. If the stack is empty, then definitely will print out, okay, stack is empty, meaning the stack is definitely at an underflow position where there is no element so far. What if the user selects option 0? If the user selects option 0, then a program will definitely close and will tell the user to press enter to terminate the actual program, because this is what we have in the condition that the option should not be equal to 0. But what if the user enters a wrong number, maybe 15, 26, 7 or anything related to that? Well, the user will be given the option saying, okay, invalid option, enter a new option if you want to proceed with this program, or 0 to terminate. Let's try to run this code. Let's try to run the code. We see if it is definitely working and how we can now tell that yes, it is a menu driven type of a stack that we are implementing using the linked list. So okay, option 1 to push in the stack. So if we say okay, option 1, definitely enter value to be pushed. Let's say 67. Then okay, we've entered 67. Let's add another value, option 1 to push in a value. Let's say okay, 33. Okay, enter another value. Let's push in another value. Let's say okay, 13. Definitely we've entered the values. Okay, so let's display now the content that is inside the stack. If we press on 3, definitely okay, stack elements are 13, 33 and 67. Enter another choice. Let's enter option 2. Option 2 to pop out an element from the stack. Popping out simply means deleting out the element from the stack, and a stack works with the principle last in, first out. Hence, the last element to be entered into the stack, which is 13, is the element that will be deleted from the stack. If we enter, okay, the popped element is 13. If we display now the content inside the stack, definitely we have 33 and 67, last in, first out. We can now even enter 0 to terminate or to exit the actual program. If we enter 0, okay, program closed, and then definitely press enter. If you want to terminate, I even press enter. Hence, this is simply the actual implementation that we can present for today, how we can implement a stack via a linked list. If you want this code, please double check the description, rewatch the video for you to understand more, because when you understand this, I mean, yeah, definitely, then you are ready to go with the stacks in C++, which is data structures and algorithm. Let's progress on our next session as we understand another type of a data structure, which is called a queue. Please don't forget to subscribe, and you are on CodeNet.